Large language models and generative AI enable exciting use cases like chatting with historical figures or answering complex questions. But did you ever wish you could use an LLM to ask questions about data that is specific to your app? Maybe you've got an app for recipes and you'd like to generate a seasonal 7-course menu based on all the 5-star recipes. Or you have a note-taking app and you'd like to get answers based on all the notes you took. Hey, I'm Peter, a developer advocate on the Firebase team, and in this video, I will show you what Genkit is and how you can use it to enhance your app with AI features that tap into your app's data. So, what is Genkit? Well, it's an open source AI integration framework that allows you to prototype, develop, test, deploy, and monitor AI workloads for your apps. That's quite a lot. So let's take it for a spin and see what this all means. To get started, you can install Genkit using npm install and then run Genkit init in an empty folder to create a new Genkit project. Or if you have the Firebase CLI installed, you can just run Firebase init Genkit. Follow the prompts to configure your Genkit project, and once setup is finished, type in Genkit start to run the project and launch Genkit's developer UI. The developer UI provides all the tools you need to efficiently develop and test AI features for your applications right here in the browser on your local machine. For example, you can use the model runner to interact with Gemini or other models. Here, you can craft your prompts and configure model parameters such as the top K or the temperature. You can also provide system instructions. Even if the model you're using doesn't support system instructions out of the box, Genkit is smart enough to prepend the system instructions to your prompt. And if you'd like to have a chat conversation with the model, you can do this by enabling append mode and adding another message to the thread. But the cool thing is, Genkit records a trace for every invocation. So if I click on View Trace, I can see the prompt I sent to the model, including the system instructions and the chat history. I can also see the response the model sent, including additional metadata such as the safety ratings. And if I want to make changes to my prompt, I can open the trace in the model runner, adjust it, and run it again. This is a great way to prototype and iterate quickly. Looking around the UI, you might notice the flows section. Let's try this menu suggestion flow to get a menu item suggestion for an AI-themed restaurant. Oops, it seems like there was a problem, and it looks like we need to provide an authentication object. I'll explain why this is in a bit, but for now, let's add an auth token via the auth.json tab and run the flow again. Aha, the sentient burger. Sounds like a witty meal. Well, I'll leave it up to you to judge the appeal of this, but let's inspect the trace to see what's happened. Here we see the input to the menu suggestion flow and the output it produced. Nested below the menu suggestion flow, you can see that the flow used Gemini 1.0 Pro to perform its job. And when we click on this entry, we can see the full prompt the menu suggestion flow sent to the model. And of course, the response. By now, you're probably wondering how this flow is implemented, so let's jump into our code editor and take a quick look. The first thing you will notice is we're using the onFlow function to define this flow. This registers the flow as a cloud function, which means we can call it from a mobile or web app. But it also means that the flow is exposed on the internet, and that is why we needed to provide an auth policy to make sure only authorized users can call it. In this code snippet, we use a Firebase auth policy, but you can implement custom auth policies as well. Next, you will notice that we define the input and output schema. This flow accepts a single string as its input, and it will also return its result as a string. Let's take a closer look at the body of the flow itself. So, first we define a prompt, suggest an item for the menu of a $subject-themed restaurant, and use string interpolation to insert the subject that the flow received in its input parameter. In the next step, we call Genkit's generate function. This function takes two parameters, the model we want to use for generating the response and the prompt. And finally, after we've received the model's response, we return the text property of the response. When we built Genkit, one of our goals was to make it easy to replace individual parts of your AI workloads. For example, if I want to use a different model instead of Gemini Pro, all I need to do is to register it in my configuration and then update this line here where I reference the model. After refreshing my browser, the new model shows up in Genkit's developer UI, and I can either interact with it directly or run the menu suggestion flow again. In the trace, we can see that the menu suggestion flow now uses the Gemma model via Ollama. And just like that, I can use a different model for my flow. Great. So now that you know how to use the Genkit developer UI, let's start building an AI workflow with Genkit. Imagine that you're building an app that allows your users to collect interesting blog posts and other articles they want to read later. But let's be honest, most of us never find time to sit down and actually read all those articles. So, how about we ask the AI to summarize all of this for us? Then, all we have to do is read the summaries, and this should save us a ton of time. So, let's start prototyping. Back in Genkit's developer UI, I craft a prompt to summarize a URL or text I provide. When I run this prompt, you will realize that while the answer sounds pretty reasonable, it contains a number of mistakes. The reason for this is that I provided a URL that doesn't exist, so the model had to come up with something. Now, you might think it was unfair of me to provide a URL that points to nowhere, but you have to keep in mind that users of your app might collect URLs of articles that have just recently been published. This means the model hasn't been trained on those new articles yet, which is likely going to lead to hallucinations. One way to keep the model from hallucinating is to include more specific instructions in the system instructions. Let's try this. A better way to achieve good answers is to provide the text we want to summarize to the model. So, if I provide a couple of paragraphs from this blog post to the model, I'll get a much better answer. And this is indeed a much better summary since it is grounded in the data I provided to the model. Now, to use this prompt in our application, I will create a Genkit flow that uses the prompt to generate an answer based on the text the user wants to summarize. I will first define a flow using the onFlow function and give the flow a name. Using the onFlow function allows me to call the flow from my client application. Next, I will define the input and output types of the flow. We want to pass in the text we want the model to summarize, so the input schema can be a string, and the result will be a string as well. To make sure only authorized users can call this flow, I will also set up an auth policy. By providing the description, you help Genkit to understand how it can call your flow. This is important for the Genkit developer UI, but also for recording the traces we saw earlier. Let's now implement the flow itself. Flows are asynchronous operations, and we define them using arrow functions, like so. The flow will receive the input in this first parameter here, and you can name it anything you like. Text seems like a good name to me. Let me grab the prompt I prototyped earlier and paste it here. Well, this is a pretty long string, so let me break it up into multiple lines. I can then use string interpolation to insert the input text. With this prompt in hand, I can now use the generate function provided by Genkit to call the model and have it generate a response. I'm using Gemini Pro, but you can use any other LLM that supports Genkit. Out of the box, Genkit supports Gemini and Ollama, and the community has already added support for other models. Once the model returns a response, we can pass the text of the response back to the caller of the flow. Just to reiterate, no matter which LLM I use, the general structure of this code stays the same. I just need to replace the name of the model. I can now use Genkit's developer UI to call this flow to verify it's working as expected. And since I use the onFlow function to define this flow, Genkit exposes the flow as a callable cloud function, and that means I can call it from my app. My client application is written in Swift, and I can use this code here to call the summarized text flow whenever the user requests the summary of an article they saved before. Here we see how this would look. The user taps on the magic wand button, and after a brief moment, they get a summary of the article. As I'm working locally, I can now go back into Genkit's developer UI to inspect the trace of this call. This is pretty cool, as it allows me to see exactly what happened. This is a pretty simple flow, but you can imagine how useful this will be once you start building more complex flows. So with just a few lines of code, I was able to add a pretty powerful AI feature to my app. All right, after I've shipped this feature to my users, some of them tell me they'd like to automatically get a summary for all the links they collect. That sounds like a reasonable feature request to me, so let's see how we can implement this. It seems like to implement this feature, we'll have to run the summarized text flow whenever a new link is added to the database. I use Firestore to store the app's data in the cloud, so I can implement a Firestore trigger. Inside the trigger, I have access to the data stored in the Firestore document. I'll add a quick check to make sure we only summarize the article if the text has changed, and then I can grab the text from the document and pass it to the flow. To invoke a Genkit Flow, I can use the runFlow function and pass along the data the flow needs to do its job. Once the flow returns, I can write back the result into Firestore. And since I no longer need to call the summarized text flow from my client app, I can convert it to a simple flow by using the defineFlow function. This way, it's no longer exposed on the internet. So now, every time a user adds a new URL to their knowledge base, this Firestore trigger invokes the summarized text flow and writes the summary back into the database. This is a really cool feature, and I am sure users of this app will love the fact they can save a lot of time by reading the summary of an article. So now that you've seen how you can use Genkit to build AI flows that you can invoke from anywhere in your app, let's take it one step further and see how we can implement retrieval augmented generation using Genkit. Retrieval augmented generation, or RAG for short, is a technique that allows you to base the model's answers on all of the data a user has stored in your app. It does this in multiple steps. First, it retrieves all the relevant data for the user's natural language query. It then takes those pieces of information and adds them to a prompt that instructs the model to generate an answer based on this data. This step is called augmenting the prompt. And finally, the prompt is sent to the model to generate an answer based on this augmented prompt. A key part of retrieval augmented generation is the use of vector embeddings. A vector embedding is a numerical representation of words, sentences, or even images. Vector embeddings represent points in a multi-dimensional space, and each point captures the meanings and relationships of the respective piece of data. A type of vector that most of us are familiar with are the geographical coordinates of places on planet Earth. Here are the coordinates of London, Paris, New York, and San Francisco. And by looking at the x and y coordinates, you can tell which of these cities are closer or further away from each other. Geographical coordinates are two-dimensional, and it's relatively easy to visualize them. Vector embeddings for LLMs typically have hundreds or even thousands of dimensions, and while anything beyond 3 dimensions is almost impossible to imagine for us humans, it's easy for computers to reason about multidimensional vectors, as it's all just maths. Implementing a RAG-based semantic Q&A feature typically requires the following steps. First, we need to compute vector embeddings for all the data we store in our application and add them to a vector store. Then, when the user wants to perform a semantic search query, we need to compute the vector embeddings for this query and retrieve relevant documents from the vector store. And finally, we can use the most relevant documents to augment the LLM prompt and have the model generate an answer based on this augmented prompt. Let's start with the first step and compute vector embeddings for any new article the user adds to their knowledge base. Genkit includes a file-based local vector store. It is suitable for prototyping purposes, but we don't recommend using it in production. You can set up multiple stores by providing a unique name. This one here is called articles. In the configuration, we can specify which embedding model we want to use. Here, we use text embedding Gecko, which is provided by Vertex AI. Later, when we want to use the vector store, we can get a reference to the indexer using devLocalIndexer ref. Just make sure to use the same name you used when configuring the vector store. Since we want to compute embeddings for new articles, we will set up a Firestore trigger that is called whenever a document is updated. We'll then get the data from the document and make sure to only continue if the full text field has been changed. Then we'll instantiate an array of Genkit documents from the full text retrieved from Firestore. Depending on the capabilities of the LLM you use, you might want to use chunking to break larger documents into smaller ones. In this case, we don't do this, as Firestore documents can only have a maximum size of 1 MB, and that is within the context window size of the Gemini model. The final step is to add the array of Genkit documents to the index by calling Genkit's index function. And with this, any new documents will now be indexed and added to the local vector store. We can now start building a Genkit flow for performing semantic search using the index we've created. Since we want to be able to call this flow from our mobile and web apps, we will use Genkit's onFlow function to expose the flow as a callable Cloud function for Firebase. The flow accepts a single parameter which will contain the user's query, and it will return the result as a string. Inside the flow, we'll use Genkit's retrieve function to retrieve all matching documents from the vector store. This function takes 3 parameters. First, the retriever we set up to retrieve data from the vector store. Second, the user's query. Genkit will use the retriever configuration to get the correct embedding model to compute the vector embeddings for the query. And finally, the number of matches we're interested in. Here, we ask to get the 3 most relevant documents. As a result, we will get up to 3 documents, which we can then use to augment the prompt. So, we'll first concatenate the documents, and then use string interpolation to insert them into the prompt. Then, we use the generate function to let the model generate an answer based on the prompt. Note that it's super easy to use a different model by replacing the model parameter with a reference to a different model. And finally, we can return the generated answer back to our app. Demo time! Let's see if what we built actually works. But before trying out the semantic Q&A feature we just implemented for the first time, I will ask the model a question it is not likely able to answer, just to demonstrate the difference. This answer looks okay, but unfortunately, it's incorrect. Once we've implemented a RAG-based semantic Q&A feature for this app, we'll be able to get a much better answer. Let's give it a try. So, I've added some more documents to the database in the meantime, and when I run this semantic search flow from Genkit's developer UI, I can see that the answers it provides are much better as they are grounded in the data stored in the knowledge base. This works great, but as I mentioned before, the local vector store stores data in local files, and it's not intended for production use at all. So, let's use a vector store that can be used in production. There are plenty of databases that offer support for vector embeddings. For example, Postgres with the PG vector extension, or ChromaDB, Pinecone, and several others. But why don't we use Firestore? It supports a vector data type as well, and this way, we can store both the full text and the vector embeddings in the same document. So, instead of using the index function to store the embeddings in the local vector store, we directly store them in the Firestore document. Notice how we make use of Firestore's vector field type to store the embeddings. The next step is to use the Firestore retriever to retrieve documents based on the user's query. Let's first set up the retriever using define Firestore retriever. It's a good idea to provide a meaningful name so it's easier to identify the retriever in Genkit's developer UI. Next, we need to provide a reference to the Firestore instance we want to use. Then, we can provide the name of the collection that contains the documents we want to query, as well as the field containing the content we want to retrieve. Vector field lets us specify the name of the field that contains the vector embeddings we computed and stored in the earlier step. Embedder should be the same embedding model we use to compute the vector embeddings. And finally, we can specify how the distance between the vectors should be computed. The default is cosine, and other options are Euclidean and dot product. Once the retriever is configured, we can use it in our semantic search function. All we need to do is replace the local vector store retriever with the Firestore retriever we just configured. And that's it. We can now use the Firestore retriever to power our semantic search feature. When adding a new document to the knowledge base, update embeddings is triggered. Genkit now uses text embedding gecko to compute the embeddings and stores them in the same Firestore document. Voila! We can now use Genkit's developer UI to perform a semantic search. The semantic search flow we defined earlier first computes the vector embeddings for the user's query, then uses the Firestore retriever to retrieve the top 3 matching documents using nearest neighbor search. Here in the trace inspector, we can see how the flow was executed. First, compute the embeddings for the query, then retrieve the matching documents, and finally, use the model to generate an answer based on those 3 documents. So this is pretty cool, but my prompt engineers have told me they'd like to iterate on the prompt. And while I have full confidence in their abilities as prompt engineers, I'd rather they'd not need to make edits to the code. Keeping the prompt separate from the code would reduce the number of merge conflicts significantly. Well, the good news is that Genkit comes with a library that allows us to do just that. dotprompt. dotprompt has a couple of powerful features that make it easier to work with prompts. First and foremost, it allows us to load prompts from .prompt files, hence the name. .prompt files are plain text files that support handlebar templates, including control structures. But the best part is that you can define both the input and output schema in their front matter. This allows you to specify the model you want to use, including any parameters such as the temperature. Let's use this to extract the prompt for our summarized text flow. Let me first create a new .prompt file inside the prompts folder. In the front matter, I can specify the model I want to use and its configuration. I use the same configuration as in my code as a starting point, but once I've added this file to my apps repository, my prompt engineers can iterate on it independently of me. I can then define the input schema. Let's start with a simple string. In the body of the .prompt file, I can now write my prompt using handlebar templates to access the input parameters. In my code, I can then update the summarized text flow to load the prompt from this .prompt file and then generate the response using the prompt. Not only does this make my code easier to read, I can now also use .prompt's advanced features. For example, structured output. Let's assume we want to tell the model to generate some semantic tags for the text it summarized. With .prompt, this is easy. First, I update the output schema in the prompt file. I tell .prompt that I want it to return a JSON object. Then, I specify the properties of this object. The first one is called synopsis, and it will contain a summary of the text. Now, you might think the description I provide here is just for documentation purposes, but .prompt actually uses it to augment the prompt it sends to the model. Pretty cool, huh? The second property is called tags, and I use it to specify that I want the model to return up to 5 relevant tags based on the content. In my code, I can now use object destructuring to extract the synopsis and tags properties from the result I receive from the LLM. .prompt has a lot more features. We're really just scratching the surface. Check out the documentation to learn how to use multi-message prompts, multimodal prompts, or how to define prompt variants. To wrap up this tour de force, let's look at deploying our AI feature to production. So far, I used local tooling on my machine, my editor, the Genkit developer UI, and the Firebase emulator. Deploying to production is surprisingly simple. All it takes is running Firebase deploy, sit back, and watch the Firebase CLI do its thing. After a couple of moments, my deployment is complete, and I can connect my application to the production deployment. Here, I add a new article to my knowledge base, and after a short moment, the document shows up in Firestore, and shortly after that, the document is updated with the vector embeddings that power our semantic search. Let's try out the semantic Q&A. Nice. This is a pretty solid answer based on the data that is stored in my knowledge base. Genkit also comes with OpenTelemetry support. This means we can now inspect the respective trays in the Cloud Logs Explorer. This gives us useful insights into how much time was spent in which part of our AI flow. Wow, that was a lot. And there are still some aspects of Genkit we didn't cover. For example, how to evaluate the quality of your LLM responses, or how to authorize users. Check out the documentation to learn more about Genkit and its advanced features. We will post more content about Genkit on the Firebase blog and on the various social media platforms. So make sure to follow us so you don't miss out when we post new content. Also, if you build something cool with Genkit, let us know. You can use the Genkit hashtag on social media or post in the show and tell section of the discussion forums on our GitHub repository. Thanks for watching. Keep generating, and I will see you in the next one.